All right, everyone. Welcome to our 9th/10th lesson of the semester. This is a makeup video since we weren't able to have class last Friday. So yeah, here's what we were going to go over on that day. So previously what we were doing was we were talking about something called improper integration, where normally our bounds are just numbers, like maybe from 0 to 1 or something like that. But what we're studying in this case is when the bounds might be something different than just an ordinary number, or something that might not quite make as much sense, like for example going to infinity. And remember, the interpretation for this is we're finding the area under the curve all the way out as far to the right as we can possibly go. And sometimes that ends up being infinity, sometimes it ends up being a finite number, and then sometimes an integral like this shows up. So let's see what's special about this example here. So we want to do the integral from 0 to infinity of cosine of x. Well, with any improper integral, we need to begin by turning it into a limit. So I'm going to send r to infinity. We go from 0 to r. And remember, the reason why we can do this is that we can put a number as our limit. That's no problem. And then we just make that number really big. That's what's going on here. And we have cosine of x dx. And then once we write down that limit, then we just focus on doing the integral here. All right, so the integral of cosine is going to be sine of x, and this will go from 0 to r. All right, so this is the limit as r goes to infinity, and then we have sine of r, and then I would plug in 0 right here. Oops, my camera's a little off here. There we go. Get that all straightened out. So normally I would plug in sine of 0 in here as well, but sine of 0 is 0. So then we're just left with this limit right here, and what does this limit do? Well, remember, the graph of sine of x looks something like this, right? It's just going to keep oscillating up and down forever and ever, so even as its input gets large, it doesn't head to any particular number. So this limit is not going to exist. It's not even going to go to infinity in this case. It's simply not going to exist because it can't settle down anywhere in between -1 and 1. So we would say that this integral diverges. And so that kind of illustrates that there's two ways you can diverge. You could diverge through oscillation by bouncing up and down and not settling down, or you could diverge by heading off to a very large or very negative number. So there's multiple ways to diverge, but you can only converge in a single way. You converge when you settle down to a particular number. That's the only way you can converge. All right. Let's take a look at this right here. We can do improper integrals where both of the bounds end up being infinite. The thing is that in order to do an integral like this, we need to actually have two different variables, or two different limits here. We're doing the limit as our bottom bound goes to -infinity, and then we're doing the limit as our top bound goes to positive infinity. Now you might be wondering, oh, why don't I just send r to infinity and then do -r and r? Well, we don't want our answer to depend on how fast these variables are going to infinity. Like maybe r is going to infinity way faster than s. We want this to be the same answer no matter what, so we should have two different variables to represent the possibility that they could go to infinity at different speeds. Because if we account for that and it ends up being the same number no matter what, then we can be sure what the area under this curve is. Anyways, this is the actual integral that we're going to do here. So then once we do that, this is going to turn into arctangent of x. And this is going to go from s to r. All right, well then let's plug in our endpoints here. We have arctan of r minus arctan of s right here. All right, now as r goes to infinity, let's remember arctangent will go to pi over 2. So that's what the first limit's going to be. And then as arctan goes to -infinity, we go to -pi over 2. But we're subtracting our second bound, so we end up with pi for this one right here. One thing to note, this was also something you could have done in Calc 1 as well. Notice that this function is always positive, so the area under the curve for a positive function should always be positive. So that's one way you can kind of check your work for things like this. All right, so it didn't make too much of a difference that both the bounds were infinite. We still end up getting a finite answer for this. Okay, now kind of along the same lines, we had 1 over a polynomial here. This is actually a particularly common type of integral, and this is called a p-integral. Well, more specifically, a p-integral is where we have 1 over x to a power, and we'll be seeing this a fair bit later here. So this p-integral, it converges based on what p is going to be. So let's take p to be greater than 1. Let's see what happens with that. So I have the integral from a to infinity of 1 over x to the p. Well, we do our limit here, like usual. And by the way, a is greater than 0, so we don't have to worry about going over and dividing by 0 in this interval. All right, so we write this as our limit, and then this is also x to the negative p. Now let's think carefully about this. So the power rule says that we raise this by 1 and then divide by our new power. And then this goes from a to r right here. All right, now let's think about this. So p is greater than 1, right? That means that negative p is going to be less than negative 1. So this is could be negative 1.5, negative 2, negative 3. And then when we add 1 to that, it's still going to be negative. So a better way to write this would be to make it positive and then just put it on the bottom. Right here. All right. Oh, whoops, this should be p minus 1. My mistake. And since p is greater than 1, this is a positive power down here. Now when we plug in our limit here, we have this constant here. So this is just some number right there. And then what's happening with this? Well, we have in our denominator a positive power, and then r is going to infinity. So this denominator is going to get very big, meaning that the limit of this first term will go to 0. So we end up with this as our answer, meaning that our integral converges in this case. All right, and then if p is less than 1, we end up having all of the same work as before, only when we get to this step, the limit as r goes to infinity of r to the negative p plus 1 over 1 minus p, and then we have our constant here. Notice that now, since p is less than 1, negative p is going to be greater than negative 1, meaning this power up here is going to be positive. And since we have a positive powered thing going to infinity on the top here, this is going to go off to positive infinity. So it seems like p less than 1 is going to diverge, p greater than 1 is going to converge. Now what would happen if p is exactly equal to 1? Well, if p is exactly equal to 1, when we do the integral, we're going to end up getting natural log of absolute value of x. So we have the limit of that from a to r. And so we have natural log of r minus natural log of a. Now we know that as the inside of our natural log goes to infinity, then log will go to infinity as well. So even though it does so really slowly, it's always kind of tapering off, it will go towards infinity, meaning that this integral will also diverge. So it seems like we're going to get this integral converging if p is greater than 1 and diverging if p is less than or equal to 1. That seems to be the result from this. This will be something that we're going to be paying attention to later. This will have an impact on the thing we're going to be learning next in class after integration. So keep this in the back of your mind as we continue. All right. So now there are other types of improper integrals other than ones that have infinity as their bound. So we can also have a finite number as our bound, and ordinarily that wouldn't cause a problem, but maybe this number causes our function to go to infinity at that point. Like for example, let's take a look at this integral right here, the integral from 0 to 1 of ln of x over x. So if I plug 1 in here, I have ln of 1 over 1. Well, ln of 1 is 0, so that's not really an issue. We just have 0 for that. But if I go towards 0 right here, my denominator is getting really tiny and my numerator is getting very negative. So something is going on here. This is going off to maybe infinity or something like that at 0. Either way, we can't directly plug 0 into here, so we can't really have this as an actual bound because the function isn't even continuous or even defined at 0. So what are we going to do then? Well, we're going to use the same strategy that we used before. We're going to define a new variable, and we're going to send that variable towards this number. Because as long as this variable is heading towards that number and isn't actually that number, that's okay. Like 0.1, 0.01, all of those are all okay to plug in here, but not 0 itself. So we're just going to send this to 0 and see what happens. Now what I'm going to do here is I'm going to send this to 0 from the right. Now why do I specify that? Why are we only coming from the right? Well, if we look at the interval that we are on here, we're on the interval 0 to 1, right? In this interval, this is where we're going to be integrating. So if I'm going towards 0, remember I'm only integrating to the right of 0. I'm not integrating over here. My integral has nothing to do with any of this. So that means I'm coming from the right here. And similarly, if for some reason 1 was our bad bound, then we would approach 1 from the left. So bottom bounds, we approach from the right, and upper bounds, we approach from the left. So this is a plus, and then that's a minus. So in this case, since it's our bottom bound, we're going to approach it from the right. All right, so then we have ln of x over x. All right, wonderful. And then now we can just go ahead and do the integral here. The way we would do this one is we would do a u-substitution. Oops, du. So this is the limit as r goes to 0 from the right of x equals r to x equals 1. And then we have, let's see, u du. So then this is going to turn into u squared over 2 with our limit from x is r to x is 1 right here. And then we have our limit as r goes to 0 from the right. If we substitute back in, we have ln of x squared over 2 from 1 to r here. All right, now if we plug in the bounds for this, what do we get for that? Oops, sorry, I wrote off to the right a little bit here. There we go. Okay, so if I plug in my bounds now, I have ln of r squared over 2 minus, ln of 1 squared, and then I have ln of r squared over 2 here. All right, now this is 0, right? Because ln of 1 is going to be 0, so we don't really care about this. Now, if I approach 0 from the right with my natural log, as natural log approaches, the input of natural log approaches 0, this will go to negative infinity. But then that will be squared, so we're going to have positive infinity, but then we have a negative out here, so then we end up getting negative infinity. But in any case, this integral is going to diverge. And it's kind of interesting that happens because there's no infinities in the bounds at all, but because of the function itself going towards a discontinuity, we can see that this is going to end up diverging. All right, now normally this would be a practice for you guys, but since we didn't have class that day, I'm just going to go ahead and do this here. All right, so we have an integral from 0 to 64 of this right here. Now 0, if I put that in, we have root 64 minus 0. Well, that's not really an issue. That's just going to be 8. But then if I go to 64, I'm going to have 64 minus 64 will be 0 in my denominator, and that's not something that we want. So that means that our limit here needs to go to 64, and since it's an upper bound, we're going to go from the left. Remember, we can't actually plug in 64 even though it's a finite number, because that would cause our denominator to be 0. Alrighty, so now let's go ahead and do this integral here. Alright, let's see. I'm going to do a little u substitution. U is 64 minus x, so du will be negative dx right here. Alright, So I have the limit as r goes to 64 from the left. Now in this one I'm going to convert my bounds to save time. So I'm going to plug 0 into here to get my new u bound. So this is going to be 64 minus 0 is 64. And then I'm going to plug r into here. So the top will be 64 minus r, like this. And then we have negative dx. So we have a negative, and then we have du over the square root of u. Now technically this number up here is actually smaller than this one, so if we flip everything in the correct order here, we end up getting 64 minus r to 64 of du over root u, if we get rid of that negative sign. Alright, and then finally we have our antiderivative here. We raise this to be negative 1/2, or sorry, positive 1/2. We divide by 1/2 to get 2. Alright, wonderful. So then let's plug everything in and then take our limit. Oops, it's 64 from the left here. So we have 2 root 64 minus 2 root 64 minus r, right here. Alright, so this is a fancy way of writing 16, because the square root of 64 is 8. Now with this, if I send r to 64 from the left, meaning that the numbers will be slightly smaller than 64, I'm going to get a positive number heading to 0. And if we have the square root of some positive thing heading to 0, well, that's going to be 0. So we end up getting 16 for this integral, meaning that it's going to converge since we got a finite number. All right. And then briefly I want to go over one more possibility. Let's say we have the integral from -1 to 1 of 1 over x. Notice that neither of these are a problem at all, -1 to 1. If we plug both of these in here, this will be defined and continuous there. So why would this be considered an improper integral? Well, it's because of what happens in the middle of this domain. Between -1 and 1 we have 0, and 0 certainly is a number you don't want to plug in here. So in order to do something like this, we would need to split this integral up into 2 pieces. We sort of break it in half and have -1 go to 0 and 0 go to 1, and then we do an improper integral with this and with this, and we do those separately right here. Now both of these integrals would need to exist in order for this one to exist. So if both of these integrals ended up being okay, we would add the results together and get that. But if even one of them ends up diverging, then the original integral will diverge as well. I just wanted to mention this case real quick because this type of integral does appear sometimes. All right, anyways, that's the end of lesson 9 here with our improper integrals. Now I want to go on to lesson 10. Now lesson 10 is called Techniques of Integration, and it's honestly more of just a review of what we've done so far. So I kind of want to just do a review of techniques of integration. Because one of the most common questions I get is, okay, we learned all these different techniques, so which ones do I use when? So what I'm going to do is I'm going to go over each of the techniques we learned, and I'm going to explain when they're useful. All right, actually what I forgot to write on this list is u-sub. And I know this is more of a Calc 1 technique here, but it's so frequent that I want to go over it again. Remember, there are 2 reasons, or 2 signs to look for with u-sub. The first is something appears frequently in the integral. So say, for example, we have an integral and there are e to the x's everywhere. Like there are e to the x's all over the function. Then u equals e to the x might be a good idea to simplify the integral. And then we also need the derivative of the substitution to be in the integral. So for example, if we had an integral with a bunch of, say, sines, we would probably want at least one cosine in there, because when we do u as sine, our du is going to be cosine dx. So we need to make sure that the derivative is in there as well. So if you satisfy both of these requirements, then u-sub might be helpful for you. All right, and u-sub is often used in conjunction with the other techniques that we're going to talk about. So it's always a good idea to kind of at least consider u-sub as an option for any integral that we do. All right, the first technique that we learned that certainly wasn't in Calc 1 is integration by parts, which a lot of people refer to as the tabular method. They're really the same thing. The tabular method is simply another way of computing integration by parts. So they're really actually the same technique in disguise, even though they seem different. So the times we should use integration by parts is when we have a polynomial times a sine or cosine, or maybe an exponential. And in that case, we're going to do integration by parts several times equal to the degree of whatever the polynomial is. So if we have like x squared times sine of x, for example, we should do it twice. If, God forbid, we have like x to the 2020, we should do it 2020 times. So it's whatever the degree of the polynomial is. When we have exponential times a sine or cosine, we're going to do this twice, and then we're going to add a copy of the integral back to the other side, which is called the wraparound method. So remember, like let's say we have the integral of e to the x times sine of x, for example. If we do integration by parts twice, we're going to get a copy of that integral in our work. And we simply move that back to the original side and then maybe divide by a number. And that's how we're going to do those integrals. Now, one really special case that I really want to remind you guys of that people seem to forget is that integration by parts is really effective at integrating like inverse functions, or what I like to think of as kind of strange functions on their own. So if you ever don't know what to do and you see just some one weird function, there's nothing really to do a u sub off of or anything, try integration by parts with u equals the whole function, and then dv will just be dx. And oftentimes this will get you where you want to go. So especially for inverse functions, but really any weird function you don't know what to do with, try to do this with integration by parts. All right. Now, some people ask me, okay, so I know there's the tabular way of doing IBP and then there's the traditional way. Which one do I use when? And my answer to that is use tabular if you know in advance how many times you're going to do IBP. So, for example, one of these, I specifically said how many times we're going to do it. So if you encounter one of these types of integrals, I would recommend just doing tabular because it is faster to do it that way. However, if you maybe get something like this, or a case that looks unfamiliar and you use IBP, for that one I would use the traditional u dv duv method for that, because you don't really know how many times you're going to do it, so it's kind of hard to know when to stop making your tabular table. So I would use traditional if you don't know in advance or if it's something strange. All right, so that's integration by parts. Next we have trig integration. So there were several different cases for this, starting with pairs of sine and cosine. So if we have sine or cosine and we have at least one odd power of them, then we're going to do a u equals whichever one has an odd power. And if they both have an odd power, then you can simply pick which one you want. So that's how we're going to do this, because we can break off one of the odd powered ones. Or no, sorry, we're going to use u equals, if they're both odd, we could use u equals either one. If one is odd and one is even, we do u equals the one that's even. Because what we do is we break off one copy of the odd powered one and use that as the derivative of your substitution for the u sub. All right, now let's say that both powers end up being even. In this case, we use the half angle identity stick to lower the powers until there's something that we can integrate, either by using maybe this method or something in Calc 1. So we repeatedly use one of the half angle identities to do this. All right, and then for secant and tangent, and also cosecant and cotangent, these are exactly the same in how they work. There end up being three cases for this. So if you ever have an even power of secant, I would recommend doing u is tangent of x, because if we have an even power secant, we could break off at least two of them and have that be our derivative for our substitution here. Now, in the case where we only have tangents, like maybe our even power of secant is 0, I would recommend breaking off two tangents at a time and turning them into secants so you can get to this case right here. So that would be what you would do if you only have tangents. All right, now let's say it's an odd power for both, then I would pull off one of each to the end, both secant and tangent, and then do u as secant, because then our du will be secant times tangent, which we move to the end. Now, unfortunately, there's the third case, which is not very fun to do. This is where we have an odd power of secant and an even power of tangent. For this one, we turn everything into secants, which we should be able to do if we have an even power of tangent. and then we keep using integration by parts and wraparound to continuously lower the power of our secant integral. So maybe we start off with secant to the 7th. If we do an IBP or wraparound, we should be able to get a secant to the 5th integral, and then if we do it again, we should get secant cubed. And then once we get to secant cubed, then we're good to go, because the integral of secant cubed is this right here. Remember, it's the average of the derivative of secant and then the integral of secant right here. So this is definitely an integral I'd recommend memorizing because it'll save you some time if you ever are unfortunate enough to have one of these case 3 integrals right here. All right, and then the key idea behind any of these trig integrals right here, for all of these cases, we use the Pythagorean identities. So be sure to know all of your Pythagorean identities, all 3 different versions of them, to help you do this. All right, speaking of Pythagorean identities, this is also the main idea behind doing trig sub. So once we know how to do trig integrals, then we can do trig substitution. And if we ever have something like this, a number squared minus a variable squared in our integral, we can make the substitution with the variable equals the number times sine of theta. If we ever have these flipped around, we could use secant instead. And if we ever have them added together in either order, we can have x is a tangent of theta right here. Now, these would technically work with cosine, cosecant, and cotangent as well, but I would recommend using these because for any multiple choice questions on the upcoming exam, we're going to be using these to get the answer. So I would recommend doing that. One very common misconception about trig sub is that you need a square root for it to work. So maybe you need to have like 1 over the square root of x squared plus 1, for example, in order to do that. But I'm here to tell you that you absolutely don't need a square root for this to work. Anytime you have one of these 3 situations, no matter what it is, trig sub is a viable option, whether there's a square root or not. Another thing is it's good to be flexible about what a and x can mean up here. For example, I think in one of the homeworks we ended up having a squared being 10, so a was going to be root 10. So remember that this technique works even if our constant isn't a perfect square. And then for the x squared, remember, this is just a single variable on its own, but remember that this is also flexible as well. So for example, if you have maybe 4x squared, your variable could be 2x. So it's just the square root of whatever thing you have your variable involved with. So all of these can be a bit more general than they initially look on paper. All right, now how does trig sub work? Well, we use the Pythagorean identities to turn it into a trig integral. We do the trig integral using one of these techniques, and then we draw a right triangle to change back to our original variable. All right, now one little tip to check your work here is that your missing side on your triangle that you solve for in this step should appear in the integral. Now there might be an extra square root or something on it, but the expression that you get should be very similar to something that you had in the integral. Also, one other point of confusion is that if you ever just have a theta, like a lone theta after you do your integral, then those will turn into some kind of inverse trig function, depending on what kind of trig function you used for your substitution originally. All right, so that takes care of trig sub, and then finally I want to go over partial fractions. And this was the last one we learned about because we could potentially need to use any of these techniques back here. So remember, there are 4 different cases for partial fractions. So the first case is where we just have distinct linear factors, like maybe this case right here. And this is by far the easiest one to deal with. We just write a constant over each factor, and then they're split over addition here. And the way that we figure out what these constants are going to be is we end up using the technique called cover-up, where we see what makes the denominator 0, in this case it'd be x equals 1, and then we cover up the matching term over here, and we plug in that x value. So we have 1 over 1 plus 1 is 1/2. That means our b is going to be 1/2. And this is by far the fastest and easiest way of finding your coefficients. So I definitely recommend doing this if you have the opportunity to do so. Now, one time you may not have the opportunity to do so is if you have repeated linear factors. So if we have something maybe like this to deal with. Whenever we have x plus or minus a number to a power, we need to make sure that we have a term for each one of those powers going up to here. So we need 1 to the first power right here, and then a square. And then maybe if this were x plus 2 cubed, we would have c over x plus 2 cubed as well. So we need one representative for each power up to and including the maximum one here. Now, we can use cover-up to get the highest powered term. Like, for example, -2 will make this be 0. So I cover up everything down there, because that's what this is. And I see that b needs to be -2. But you cannot use cover-up on any of the lower powered ones. So we can't use cover-up to get a. What I would recommend doing for that is plugging in another number besides this and then solving for a once you get b. So for example, we could plug in x equals 0, perhaps, and then solve for a by doing that. So that's another way of getting our coefficients. All right, the third case is where we have an irreducible quadratic. Like, we can't factor x squared plus 1 further down, so we just have to live with it. So in this case, when we have an irreducible quadratic in the denominator, we have two constants up top, and one of them has an x attached to it. So the partial fraction decomposition for this is a over x minus 1, bx plus c over x squared plus 1. And the way we do this, the way we figure out what all of these are, is we use comparing polynomials. Because we can use cover-up to get a, but we can't use cover-up to get b and c. So the way we do that is we clear the denominator, FOIL everything out, and then the polynomial on the left should be the same as the polynomial on the right. And if you set the matching coefficients equal to one another, then you'll get equations for your a, b, and c, and then you can solve for them. All right, and then the final case here is similar to case 2, where we have repeated irreducible quadratics. So if we have x squared plus 1, but then that itself is raised to a higher power, kind of like how we did back here, we need a copy of this term for each power going up to this one right here. And this especially is the time we want to use comparing polynomials, because for this example right here, we can't use cover-up to get any of the 4 of these. So comparing polynomials is especially powerful for case 4 here. All right, so I want to give you guys some tips on doing partial fractions here. One thing to kind of watch out for is when you actually don't need to use partial fractions. So if you only have a single factor on the bottom and a relatively low power on the top, if you do PFD, what will happen is you'll actually just get back to where you started. So say I want to do PFD on this because it's a rational function. I would come over here and I'd be, wait a minute, a would be 0 and b would be 1 if I compared polynomials here. But then that would just get me back where I started. So for something like this, you have to use another technique. Usually completing the square on the bottom will probably be a good idea for that one. All right, and then for doing a lot of these integrals, this is a useful integral to know. So 1 over x squared plus a number squared is 1 over the square root of that number, and then arctan of x over the square root of a squared plus c. So this is a very common integral to see, and you can save a lot of time and trig sub energy doing this right here. Finally, don't forget to include your parentheses when you multiply and clear the denominators here. So for example here, if we multiply both sides by x squared plus 1 squared, we would have an x squared plus 1 times this ax plus b. But it's really easy to just have b written times that and then ax on its own. So don't forget to put parentheses around these guys when you clear the denominator. Finally, one thing I didn't write down here is that the number of coefficients you should be solving for is equal to the degree of the denominator. So you can see that in all of these examples actually. So if we were to FOIL this out, this would be x cubed, and then we have a, b, and c. If we were to FOIL this out, we would have x squared, and we have a and b. If we were to FOIL this out, we would have an x to the 4th, and then we have these 4 right here. So that's a way to make sure, or at least see if you're on the right track for getting your coefficients set up correctly, if you have the same number of them right here as you do the degree of your bottom polynomial. All right, so these are kind of my general tips on how to do each of these methods and when they may be useful. And ultimately, the best, just like the rest of mathematics, the best way to get better at integration is to practice. So there should be a integration techniques homework that you can work on, and that's just going to include some integrals for you to practice. Anyways, all right, so that's lessons 9 and 10. So I'll post this video as soon as I can, and then hopefully you guys can get caught up here. So yeah, I'll see you all in class.